In this lesson, we are looking at graphical solution of equations. Now, the thing about this is that it's one of those things that can be asked in all sorts of different ways. And there's sort of a limited amount of teaching that can be done. So what we're actually going to do for this lesson is to work through past paper questions, to actually see how these things work. So you've got a good idea of the techniques that you're going to use. Now let's apply them. What I have done is I've already started each of these questions so that you don't have to go through that drawing of the graphs. What we're going to do is actually go on to the subsequent pieces of these questions when we're actually using our graphs to solve equations, when we're working a little bit more with those graphs. So in this case, we've got a graph of y equals 3x plus 2 over x squared plus 1. And it was a couple of values to calculate using that equation and then drawing a graph. We've got that grey block is in the middle, so we've got a discontinuity in the graph, and we end up with two separate sections. You, of course, would not have wobbly lines when you're doing this on paper. It would look a lot more beautiful, but this is good enough for us to work with on screen. So the first question part of this one asks us to write down the value of the largest integer k, so that the equation 3x plus 2 over x squared plus 1 equals k has exactly one solution. And the thing to always look for and circle is your curve. This is the equation of the curve that we've drawn. So we want to say where it equals k. Now it's got to equal a single value, right? So remember, this side would be the line. So we would have a y equals k. So y equals 2, y equals minus 5. Okay, those are all horizontal lines. So we say, if we put a horizontal line across our graph like that promise it is horizontal. How many solutions do we have? We have only one solution, because the solution is found at the point of intersection. If we put a horizontal line across up here, now we've got two intersections, so we have two solutions. Now the thing they want to know is, what's the largest value of k for where we have exactly one solution? So definitely not at the top here. But we could put a line across here. That would give us one solution. So how high can we go? Well, we look nicely at our curve and we see the more than one solution starts here. If we put a more accurate horizontal line across here, we hit the curve more than once. More than one intersection means more than one solution. So we have to work down from there. So what is the largest integer is the first integer we bump into as we move down. So our scale is working on 2 blockies for 1. So working down from here, our largest integer is actually named for us. It would be 5. So the largest k value here would be 5. Take our scribbles off because we're going to use this graph again. So if k is 5, we have only one solution. If k is less than 5, we have only one solution. If k is more than 5 integer values, then we're going to have more than one solution. Next part of the question asks us, by drawing a suitable straight line on the grid, solve 3x plus 2 over x squared plus 1 equals 15 minus 3x. And again, we go in there and we say, that there is our curve. That's what's drawn on there in that grey line. So in order to solve an equation, we need to look for intersections. So if that is our curve, then the other side is our line. So our line is y equals 15 minus 3x. Now normally we put these in, y equals mx plus c, to make them easier to work with. So y equals minus 3x plus 15. Now we know exactly who's who, and we're not going to have any sort of weird and wonderful misunderstandings about what's the gradient and what's the intercept. So intercept is 15, gradient is -3. So down 3 over 1. So we head up to our graph. Now we've got to plot this line in order to be able to see where the intersections are. So we said that our y-intercept is 15. So we find our y-axis and we go up to 15. Then we said our gradient was -3. So down 3 and over 1. So down 1, 2, 3, because we have to be accounting for our scales, and over 2, 1 puts us here. So then we take our ruler, and remember we always draw these lines from one side of the plot area all the way to the other side of the plot area. Wish me luck as I do this without a ruler. My deck is going very squonk. Let's try this. And something like that. So yours, of course, would look far more beautiful, far more straight, and would be done with a ruler. But you get the idea. This is the line that we are going to call y equals -3x plus 15. So now we can use it to solve the equation. Curve equals line, where they intersect. And look at this, we've got 1, 2, 3 spaces for answers, and we have 1, 2, 3 intersections. So now we've got to read off those values for x. So off the x-axis. So our x-axis is going 0.1, 0.2, 0.3, 0.4 up to -1 and so on and so forth. So if we start with this top one, it's going to be easier just to count from the y-axis up here. So there's our y-axis, there's our intersection. So -0.1, -0.2, -0.3, -0.4 would be our first one. Then we head back to our graph to get our second one. There is the intersection. So 0.1, 0.2, 0.3, between 0.3 and 0.4, so 0.35. And the last one, quite a lot further over, so we're going to read him by going down. So our intersection is here, heading down to the x-axis. There is our 2, so 2.1, 2.2, 2.3, halfway between, 2.25. So we're not doing any actual calculations to solve this equation. What we're doing is using the graph to solve it. This is why we call this graphical solution of equations. Because the wonderful thing about graphs is that when you have different graphs, you can actually use intersections between them to solve equations. Fantastic. So we're going to move on to another question. Here we have values for 2x cubed plus 4x squared. Again, sum to fill in using the formula, complete the table, and then draw a graph, which I have already done. And again, a note to yourselves, your graphs will look a bit more smooth and accurate when you're doing them with a pencil on paper. I am taking the big excuse of doing these digitally on screen. It's not nearly as easy as it is when you do them by hand. So we've set ourselves up. We have a beautiful cubic graph, up, down, up, and we head to the questions. Find the number of solutions to the equation 2x cubed plus 4x squared equals 3. Same thing again, always the same approach. That there is our curve. So this here is our line, which would be y equals 3. So it's another one of those beautiful horizontal lines. So we go to y equals 3 and we consider the line across at y equals 3. Now they asked us just for the number of solutions, not the value of the solution. So we're just looking for the number of times that our line hits our curve. How many times do they intersect? And we can see it is just the one. So the number of solutions to that equation is 1. And in this case, I'm going to write it out as a word. There's nothing wrong with a word or a number, but a word makes it more obvious. I don't think that the answer is x equals 1. Okay, I know that I'm just saying one solution. I'm giving an answer in English rather than in maths. So if we move on, we've got some more questions relating to this curve. So the first one here says the equation 2x cubed plus 4x squared minus x equals 1 can be solved by drawing a straight line on the grid. Write down the equation of this straight line. Now remember, first identify your curve. Your curve is this bit only, 2x cubed plus 4x squared. So in order to be able to solve an equation, we would need to have curve equals line. Well, we don't have that at the moment because we have this problematic minus x who's stuck on the wrong side. So we need to move that minus x onto this side. So 2x cubed plus 4x squared minus x plus equals 1. We're going to have to add the x here to remove him and pop him up on the other side. So then we would have 2x cubed plus 4x squared equals x plus 1. Now we have that relationship. Curve on its own on the left, line on its own on the right-hand side. So the equation of our line is y equals x plus 1. They then ask us to use our graph to solve that equation. In order to be able to do that, we're going to have to plot the line. We have to plot our line so that then we can look for those intersections. And there's a clue here, we should have 3 answers. So y equals x plus 1. So our intercept is 1. So we head to our y-axis to 1 and we mark. Now we're going to go a gradient of 1. So up 1 and over 1. So from 1 to 2 and from 0 all the way to 1. So that's our second point. And we take our ruler and our pencil and we draw a beautiful straight line across the entire piece of graph paper. And you all just wish me luck that I can do something roughly accurate enough to get us a decent answer for this lesson. Okay, slight wobble, but you get the idea that this is representing a beautiful straight line. Okay, and as expected, we have 1, 2, 3 intersections for our 3 solutions. So now we've got to have a look at these intersections because we need to get what are the x values relating to those intersections in order to solve the equation. So starting here with this one, let's check our scale. We're going -2 to -2.5 over 10 blocks. So a 0.1 is actually over 2 blocks. So if we bring this one up to the axis, these are -2. So -2.1, and that would be -2.2. So -2.15 is our first solution. Our second solution is this intersection here. So let's bring that down to the x-axis and figure out where we are. So there's a -0.5, so we're moving this way. We're bang on -0.4. So our second solution, -0.4. And then our third solution is the third intersection. So we bring that value down all the way to the x-axis. And we see we're not quite on the 0.5, but we're not on the 0.6 either. We're in between. So we're on a 0.55. So we're just reading all those solutions off our graphs. Now the thing is, of course, there is some degree of variation. Even if we all draw these things beautifully well, there will be variation. So the memos for these kinds of answers do give a little sort of, you can say 0.35 to 0.6. Okay, they will give what do I mean? You know what I mean? When they don't give you one exact answer only, there's a range. There we go. There's a range of answers that's acceptable. But you do need to be careful with your graph because that range of answers is not enormous. That range of answers is based on standard graphs. So you do need to be as accurate as possible so that you do land within that range of acceptable answers. So we've got our three solutions. Then we now to look at the last one. This is quite an interesting question. They ask us, the tangent to the graph of y equals 2x cubed plus 4x squared, that's our curve. That whole thing is our curve, actually. So we're back just to looking at our curve. Has a negative gradient when x equals k. Okay, so where on the x-axis do we have a negative gradient? Complete the inequality for k. So k is between two values. So if the tangent has a negative gradient, it means that the curve also has a negative gradient. Because remember, we use the tangent to estimate the gradient of the curve. So if we look at our curve, we go up, down, up. If we translate that into gradients, we go positive, negative, positive. So we need to say, what are the limits of that negative zone in the middle? So the right-hand limit is easy. It turns there at 0. So we need to find here, where does it turn? So at the top of this bump. So just about here. If we bring that down, what's our x value? Well, there's a minus 1.5, which means that's a minus 1.4. So between a minus 1.4 and a 0, our curve has a negative gradient. So k is between minus 1.4 and 0 is our final answer. Because if the tangent has a negative gradient, so does the curve. Our last question is slightly different yet again. I told you there's a lot of variation in these questions. Okay, so here, the diagram shows a graph of y equals fx for minus 2.5 less than or equal to x less than or equal to 2. So this looks rather familiar. It's an odd-shaped graph. It's going up and down, okay? But now we're using y equals fx, so we're bringing in function notation as well. So they've drawn it for us. This question is all about understanding what's going on and working with this graph. So the first thing they say is find f1. Now remember, we've got y equals f of x. Well, if they've put a 1 in where that x belongs, we know that it's x equals 1. So what does the function equal when x equals 1? What does y equal? So when x equals 1, let's just line up with the middle of the graph so it's a bit easier. There's our x-axis, there's our 1. So in order to know what y equals, we need to go down to the curve in this case, and across we need to read that value off. So what is our scale going down? Here we go from minus 9 to 10 in 1, 2, 3, 4, 5 blocks, so it's 0.2s. So there's our minus 1, minus 1.2, minus 1.4. So f of minus 1 is minus 1. F of 1 is minus 1.2. The value of y when x is 1. Then they tell us, solve fx equals 3. But remember, we know that y equals fx. Okay, So we have our curve. So fx is our curve equals 3. Now this looks familiar because we've been boxing curves for the last 2 questions. So we want to know, when does our curve equal 3? So back up to our curve. Here's our equals 3. So there is our intersection. We come down to our x-axis. Our x-axis, we're going all the way to a -1 in 10 block years. So we are going 0.1, 0.2, 0.3, 0.4, minus 0.5. So x equals minus 0.5 when fx equals 3. And if you think about it, if we put in minus 0.5 into here, if we said f of minus 0.5, and we went back like we did for the first question, we put in minus 0.5, we'd go up and we get 3. So it's a lovely way to check your functions backwards and forwards. Next one. The equation fx equals k. So curve equals k has only one solution for minus 2.5 less than or equal to x less than or equal to 2, which is what we've got wrong. Write down the range of values of k for which this is possible. So where on this graph do we only have one solution? We have to zoom out a bit to see the whole thing. Remember, when it says fx equals k equals that horizontal line. So where can we put a horizontal line and only get one solution? Well, there's lots here. All this top section. It's only when we get down here that we start getting more than one solution. So where exactly do we get that more than one solution? It is exactly at -4. See, now we've got 2 intersections. So as long as k is bigger than -4, then we only have one solution, which is what they wanted. The range of values of k is greater than -4. That will give us only one solution because it would be intersecting only once. K is less than -4, we would have more than one intersection, so we would have more than one solution. The next one asks us, you see there's starting to be a pattern in here. By drawing a suitable straight line, solve the equation fx equals x minus 5. Well, fx here is our curve. So this is our line. We want y equals x minus 5. So the intercept is -5, the gradient is 1. Back to our beautiful curve. The intercept is -5. The gradient is 1. So up 1 and over 1. There. And then with a ruler, drawing a straight line all the way to the edges. So y equals x minus 5, and the solutions. And again, we've got that wonderful double check, 1, 2, 3 solutions, and 1, 2, 3 intersections. So we established that our x-axis is going in 0.1s, and we know that this is a minus 2.5 to 2. So minus 2.5, minus 2.4, minus 2.3 would be our first answer for that first intersection. The second intersection, ooh, that one's a bit more tricky, so I think we're going to have to bring him up all the way to our x-axis to read it a bit more accurately. So there we have our 0, our -1, so minus 1.1, minus 1.2, so minus 1.15 between them. And our last intersection getting quite far down. So we'll bring it up to the axis to read it. So there's our 1, 1.1, 1.2, 1.3, between 1.3 and 1.4, so 1.35. So the last one asks us to draw a tangent of y equals fx at the point where x equals 1, and therefore to estimate the gradient. So at x equals 1, we come down to our graph. This is the point at which we are drawing our tangent. And our tangent wants to be a lovely big triangle. So remember, the best way to do this is actually to have a clear ruler, and then you can wobble your ruler so that it sits nice and against your curve, and then you can get your 2 points and you can estimate your gradient using those 2 points and that wonderful, wonderful formula of gradient equals y2 minus y1 over x2 minus x1. We have run out of time to complete that calculation in this lesson, but it's a tangent calculation, not a graphical solution of equations calculation, so it's not too much or train smash. Please make sure that you are happy with this concept of solving equations by using graphs, of drawing additional lines, of rearranging equations so that you've got things that match your curve equals line concept, so that you can then look for those intersections to find solutions.